Good afternoon. My name is David Glaubman. I work for Risk Management Solutions, which is a catastrophe modeling firm in California. And I'm here to talk about my experience in developing two domain-specific languages to be used for modeling insurance and reinsurance contracts. So some friends and colleagues suggested that it's good to tell a story. So it was a dark and stormy night. It was actually several dark and stormy days and nights in New Orleans and the Gulf Coast cities and towns. Hurricane Katrina hit in late August of 2005. Almost destroyed the city of New Orleans, caused, that was mostly due to flooding from when the levees broke. Almost 2,000 people lost their lives. Tens of thousands of people lost their homes. It was $125 billion in property damage. So that's 9 zeros. I guess, is that milliard here or billion? Anyway, it's billion in the US. So it was a terrible tragedy. It was also, economically, it was a tough day for insurers who are our clients. There was $60 billion, almost half of that, $125 billion, in insured losses, and there were almost 1 million insurance claims filed, just coming from that one event. So my employer, RMS, helps insurers manage their catastrophe risk, and I'll be talking about one part of that in what follows. So insurance companies are, what insurance companies do is they pool many risks, and for things that are independent, like, in other words, if I smoke and get lung cancer, it doesn't make you more likely to get lung cancer. These are independent things, and therefore, if the more people they insure, the more they can have a smooth loss experience, and it actually reduces their risk. They bring in more premium, they'll pay out more, but there'll be less fluctuation. This is due to the law of large numbers, which provides diversification effects via pooling of risk. So catastrophes are like the horror show for this, because the risk is highly correlated. If my house is hit by an earthquake, and my neighbor's house is probably in a lot of trouble. So this curve here, the exceedance probability curve, is one of the tools insurance and reinsurance companies use to manage their risk, their catastrophe risk. If you look at it, basically along the x-axis, there's loss, which goes from 0 to many billions of dollars. And along the y-axis is probability. And any particular point on that curve is the probability that that P sub I is the probability that the loss exceeds L sub I. And so for catastrophes, this thing goes out a very long way. It's one of those long tail things. So maybe if that's $1 billion, that could be 40 billion, and or 60 billion in the case of Katrina. So it's a little complicated, and I don't fully understand, because it's a trade secret, how exactly the insurance companies manage their risk. But from this curve, if you can calculate it, you can, for example, like if P of 0.01 is the 100-year return period, the one chance in 100 that my loss will exceed a particular amount. And so there's a number of statistics, but that particular one you can just read off of a point on that curve is something where a risk manager at an insurance company might say, okay, we're going to manage to the 100-year occurrence exceedance probability, that the chance that I'll lose more than, say, I don't know, $5 billion in 1 year. And so they try and manage their portfolio of insurance and reinsurance, which is sort of laying off some of their risk to be able to hit that. So the trick is, how do you compute that? And so my company and a few others have developed catastrophe models to compute this curve relatively efficiently and relatively accurately. Every time there's a new major catastrophe, everyone recalibrates their models because it isn't quite right. So I'm not going to talk much about this, but basically a CAT model has a whole bunch of physical simulated events. It's called a stochastic event set. It's like various landfalls of hurricanes based on wind speed, and it's basically a field with the wind speed and direction of the wind for a hurricane. And they use those events and hit these models of buildings based on some fairly simple variables describing what the building's used for, how it's constructed, how tall it is, what the soil is, for example, what the soil type is if it's in an earthquake area. And that's called the vulnerability model. Out of that comes probabilities of damage. And that's fed into the financial model, which computes the loss to an insurance contract that's covering that building or buildings. So this technique, and this is probably about 30 years old. RMS is 30 years old. Our main competitor is 30 years old. And our software is 30 years old. And so around 10 years ago, this is actually what our model of exposure was about 10 years ago. I'll speak to it in a second. But so our software was very useful to people. It was productive and mature, and maybe it was a little quaint. It was difficult for people to use. It was difficult for us to change. I wouldn't call it a big ball of mud, but it was, I mean, I remember asking the guy who was the chief actuary at the time, well, how is a particular financial mechanism, how is it supposed to work in RiskLink, our product? He said, oh, well, yeah, you better run it and see. I mean, people don't, the way to describe the product was to try it out and see what it did. It was fragile. Meanwhile, simulation was becoming mainstream. It had long been, high-performance computing in supercomputer centers, but between Hadoop and a number of other distribution techniques, they were becoming the sort of thing that our clients would be able to run. Finally, our exposure model, exposure is the description of the things that are at risk. So in the case of property insurance, it's the buildings and the contents of the buildings and various types of loss that can result from damage to buildings from these perils. And these pink bits here is where all the insurance was. It was in like 14 different tables. Now some of these tables are describing like buildings. So, a building would have a floor of this type, so many square feet, and a deductible. And I remember asking the VP of software, well, buildings don't have deductibles. Buildings have, walls and bricks and mortar. And he didn't even see that was a problem. But I felt it was. And I convinced him of it, and he said, well, it'll take, 5 years to change. And, well, it took 10, but we changed. So this is not good, right? It's like, there was a good reason why they did it originally. Originally, there was only one, all those things on the left, there was only one of them, because there's one for every peril. But, and then these others, just as they added more types of insurance, they had to add more tables and more relationships between tables, and it got messier and messier. So at the same time as we have simulation coming in, which means instead of distributions, we're going to sample those distributions, and then we're just going to have, a loss of, say, instead of a beta distribution with a mean and standard deviation, we'll have a loss of, $50,000. And it's going to be a lot easier to calculate the insured loss on $50,000 than on a probability distribution. So between, as I say, simulation and the fact that our customers were really, well, we have all this, your insurance, you're not modeling it too accurately. We have these more advanced contracts, and we need to compute this EP curve, and we need to compute it quickly. We need to compute it. Any given EP curve doesn't take that long to do, but if you have 1 million houses covered by 1 million contracts, and you want to compute it not just at the portfolio level, but at all these various county levels and by line of business, and there's a lot of calculation. It takes hours, sometimes it would take days if you had a fine enough granularity of calculation, a large enough portfolio. So for all these reasons, we looked at, can we come up with a better way of representing and computing the payout of contracts? And the reason, so remember, we're trying to compute this EP curve, right? This thing here. And to do that curve represents, actually I should say something about that. If I may have pressed the wrong button there. But that curve represents, in simulation, it's almost trivial to build that, because you just kind of order all your losses from smallest to biggest. And then there's two ways of doing it, but the way I found it easiest to do it is you have all the losses of all the trials that you run for each contract, or whatever you aggregate it to. And then you just kind of create a whole bunch of buckets between your smallest loss and your largest. And for each loss, you just sort of put you just sort of count. Let's say it's $100,000. I put a counter in all the buckets up to $100,000. And when you do that, you just get a histogram that gives you exactly that curve. So rather than calculus and analytic methods, it's very simple if you can do the simulation and compute the payout of the contract quickly and accurately. to generate this curve, which is what our customers need to be able to manage their risk. Okay, so when last week's episode, we talked about the fact that we were looking at trying to come up with a new financial model, a new way of representing and computing contract losses for insurance contracts that would be fast, efficient, and accurate. So we had to learn the language. We were dealing with relational tables. The code was extremely difficult to unravel, and there was a lot of it. It was 600,000 lines of code. She was dealing with calculus and, as I say, these probability distributions. So, we looked for experts. The experts we had in the company tended, and even in our clients, were experts at dealing with what was then a 20-year-old program that, RiskLink, our flagship program, rather than so much dealing with insurance. I mean, in other words, somebody was writing the actual insurance contract, but the CAT analysts, the catastrophe analysts, were dealing with how do we go and represent that as well as we can in these relational tables and based on what this somewhat opaque financial model did. So, we talked to people, we looked, read books old and new. We looked for common contract wordings. We tried to get contracts from our customers, which was also a lot harder than I expected. I think, anyway, I think there's several reasons for it, but to some degree, it's their secret sauce, I guess. It would have been very helpful to them and to us if it had been easier to find it. But we managed to get, a pretty good selection over time of contracts. And we looked for, common wordings and tried to understand what they were. Then we would go and talk to some of our experts and say, okay, what exactly does this mean? What exactly does this do? Right? And so here you see we have this talk of a layer, a primary layer, and an excess layer. And this 30% of 100% of USD 50 million is a description of one layer. The excess layer is 50 million, excess 50 million. So we had this hypothesis that we could represent these contracts basically as a collection of layers. If you look at the contracts, they're just, they're not in any particular order. They're just sort of, well, here's our limits of liability, here's our special conditions, here's what's excluded. It was just sort of a jumble of, sometimes dozens, in very large cases, hundreds of pages of verbiage. But this seemed to be something that, and insurance is a global market, right? So that people write these things somewhat differently, but then they go, and particularly if they have to get reinsurance, they go through a handful of these brokers who are part of the global reinsurance industry. So they, even though there's differences in the words they use, the language isn't always the same. It's understandable to each other because they have to trade this risk. They have to, buy and sell these contracts with people in other countries and other markets. So our hypothesis was that we could build a contract out of layers, and we came up. This was trying to really understand what this language was and to disambiguate it. And there's places where there'd be 3 or 4 words for the same thing. In England it was called one thing, in the US it's called something else, in Bermuda it's called a third thing. we would make a choice and say, okay, that's what we're going to call it. And so we came up with this contract definition language, the first of the languages I'm going to talk about. And you can see there's some similarity, right? So we're giving it a label primary and saying it's 30% of 50 million. So that means that of the first $50 million of loss, I'll pay 30% on the dollar. The other one has a label first excess. And this one says, for the next $50 million of loss, so if it's $60 million of loss, the first one is going to pay 30% of 50 million or $15 million, I guess. The first excess layer is going to pay 100% of everything between 50 million and 100 million, right? It's going to pay up to $50 million. In this case, if it's a $60 million loss, it's just $10 million. So, you know, conceptually, this is very simple, right? There's this thing we call an attachment point. That's where the thing's, you know, is excess of, like in that case was $50 million. There's the limit, which is what's the most it can pay. And there's the share, what is the percentage to pay. So this is the geometry we basically came up with. And in this case, I'm sort of merging those two layers because I wanted to show all three parts of the geometry. If you have 30% of 50 million excess 50 million, it's that sort of rectangle in the upper right, which is it's 30% of the distance of the width of the rectangle, starting at that $50 million attachment point. So it's a pretty simple and straightforward thing. That didn't look right. And I don't know why. Let me end the show and just show you what the thing actually looks like. Huh. That sure looked fine half an hour ago. So, so that's that is a rectangular selection from a PDF that basically says in legalese or contractees, 2.5 million British pounds every occurrence, and in the aggregate to losses in the Netherlands by flood. And then I cleverly turned it into what we would say in CDL, which you can read. So meanwhile, back to so, you know, we were happy, right? Everything is a layer. It's very simple geometry. We just sort of, I've only talked about half of it. There's the term and then what the term covers. Like in the case of that illegible blob there in the previous slide, that was losses in the Netherlands due to flood. So you may have a contract that's covering everything in Europe for various perils, but that particular layer only applied to Netherlands flood. So we were pretty happy with this. Everything we tried gave us the right answer. And then we went and hired this VP of product management, and he had been a chief actuary at an actual insurance company. And we're talking to him about it. You know, we were pretty excited about, you know, look at what we've done here. And, you know, he said, well, you know, yeah, that's almost right. You know, but it's not quite right. And this was actually a great thing. And it was the fact that we had this very simple model that we could explain to him and show him, and that he pointed out, you know, where we made our mistake. And so we made our mistake because we thought all these words, right, in the language meant the same thing. So we chose one and implemented it. And this gave us the right answer for everything we tried. But it turns out that even though Google may say, it's the same thing, it's not actually the same thing. And so we thought these all meant the place where the coverage starts. Remember in that picture of the geometry of the layer, it's that first part where you're not paying anything. So he said, no, that's not quite right. A deductible is not an attachment point because deductibles and sublimits, which are sort of the other kind of thing that restricts or gives a haircut to the incoming claims, don't actually provide any coverage. They don't pay anything out. What they do is they reduce the claim and then you pass them to the layers, we got the layers right, that do provide coverage. So he gave us this very simple algebra in the sense of, 8th grade algebra, that S is your subject, your incoming claim, and then if you have a deductible, that will give S a haircut by increasing this value D. If you have a sublimit, that can give S, reduce S, by increasing this thing X from the top. And then what actually, the effective claim that goes into your coverage is S minus X minus D. Well, I said, wow, this is great. I mean, it took me a couple of days to sort of give up on the fact that not everything was a layer. I mean, I was really pretty happy about the simplicity of that. But eventually I sort of gave in to the reality of it and said, well, that's easy enough to do. And we did. And plus we now had this very simple, I mean that equation is pretty simple to compute. And so we refined the model. We added two things to our language, sublimits and deductibles. So this sublimits is that one that was on the slide that was the top part was illegible. That I have a sublimit of 2.5 million British pounds in the aggregate, meaning that's not just on this occurrence, but across all occurrences during the course of the contract, cannot exceed $2.5 million to a Netherlands flood. So that is actually just like, or I'm sorry, it's not quite in the same syntax as the cover, which is the thing that provides coverage. It's this thing that is give me a haircut from the top, saying anything over $2.5 million of loss to Netherlands by flood, we're going to cap at 2.5 million, and then it's going to go into that cover there. Meanwhile, other losses that aren't from Netherlands or aren't flood, flow directly through the cover. They're not reduced by this term. So this is that sublimit. I just showed this is the actual code. It's just a lambda that, as you see, I mean, SDX is just an array with 3 numbers, and X, S, and D are the indexes. This is like extremely fast code for computing this thing. I mean, this was something that was pages in the old, admittedly analytic solution. So by refining our model, a couple things. One, by having a language and compiling away, sort of all the stuff that doesn't matter until you just get basically these opcodes that, you just get this list of opcodes and then various a few arrays of indexes as to what exactly the opcodes cover. You can compute now this contract payouts for a vast variety of contracts extremely quickly. And in particular, well, we could, our inner loop was basically, I just looked at it before this talk. It's 84 lines of code that actually computes all the terms in a contract, and these are the kind of terms that it computes. It still sort of boggles my mind how simple we were able to do by we were able to strip out the accidental complexity that didn't affect how we computed, how we computed these losses, because we weren't interested in various other aspects of the contract. We were interested in what does this contract pay out if I get these claims. We're not interested in are those claims valid or not valid. We assume they're all valid, but we just want to be able to help our customers compute this EP curve, and to do that we need to be able to represent any contract they want and compute the output. So meanwhile, back in New Orleans, our insurance companies are having a tough time. $60 billion of insured loss and 1 million claims from a single event. So one question is, why didn't the insurers go under? I mean, as far as I know, I think one reinsurer may have gone out of the business of reinsurance. I don't think they actually went into insolvency. And 3 of them were downgraded in their rating for 18 months. But a lot of the insurers just didn't want to write homeowners insurance in Louisiana anymore, because they'd had a tough year. They lost way more they had to pay out than the claims they were going to get for the next 50 years. But they didn't go out of business. And why? Well, they had reinsurance. I mean, they had various things, but one of them was reinsurance. So I mentioned this before. Reinsurance is insurance for insurers. So it reimburses the insurer when the insurer pays out a large loss. There's sort of a side agreement between the insurer and reinsurer that the reinsurer will take some of that premium, but will pay the insurer back some of that. Will reimburse him for some of that loss, try and make him whole. So it really is just like insurance on insurance. And unlike an insurer who tends to, these are admitted for insurance within a particular state, right? And so you're very concentrated. And so these things that are regional, like a hurricane or an earthquake, can really wipe you out. Reinsurers are global, and they can try and diversify by taking things that really are uncorrelated. Like they'll take some hurricane risk and maybe balance it off with some, in the example here, I say a Japanese earthquake. Now, in a bad year, you might get a Japanese earthquake and a Gulf Coast hurricane, but those are the breaks of insurance. It's not like, those are uncorrelated things. Those are independent events, and every so often you get 2 independent events bad, but that's not a catastrophe kind of thing. The catastrophe is you have this huge correlation. So reinsurers are able to do that. So as I said, reinsurance is insurance. Therefore, and reinsurers deal with large, sort of the whole portfolio that an insurer has may be covered by a reinsurance contract. So they manage their business using a lot of the same tools and techniques, in particular this EP curve, for their losses, for the losses of their reinsurance contracts. And in fact, they're the people who, most of our revenue comes from reinsurers, not from insurers at RMS. So when we thought, well, you know, this CDL, this contract language we're developing can work for reinsurance as well, you know, management said, okay, maybe it can, but make sure it works for insurance. And, you know, and we said, okay. But then it, you know, came time to, okay, now we've got to deal with, you know, the hard part, which is our major business. And our intuition turned out to be true. We could efficiently compute the, we could represent reinsurance contracts in CDL in the contract language. And as a result, we could very efficiently compute losses. And as a result of that, we could very efficiently compute these EP curves, which is what our customers needed to be able to get the stats by which they manage their business. So that's good. That's good. We were lucky and happy about that. But we had a problem that we still had to solve. So we can represent any given reinsurance contract just the way we would a regular contract, but reinsurance contracts are unlike almost all insurance contracts in that they're usually written as these general things called treaties. So a treaty, like an insurance contract, you know, covers your house or you know, the 15 you know, or this building or, you know, a hotel chain. Whereas a reinsurance contract will tend to be between an insurer, who is called a cedent by the CEDANT, by the reinsurer, who cedes or gives some portion of their risk to the reinsurer. And it's not, at the time you write that treaty, that contract, you don't know what those insurance contracts are because they haven't been written yet, right? So what it does is this treaty sort of specifies, well, we'll cover all the contracts that satisfy these conditions, like they're commercial business, they're in New Mexico, maybe some other things. They only cover things between $2 and $5 million, or you know, various conditions. So it's kind of tough, or tougher, to describe, to form exactly what the subject of that reinsurance treaty is, because it's not any one contract, or necessarily even the loss of any one contract. It's possibly millions of contracts and some part of those millions of contracts. So there's another thing I won't get into much because I think I need to talk faster, is that there's something called inuring, where one treaty inures to another, one contract inures to a treaty, which means basically that they both cover the same thing, but this one pays first. It's kind of primary to the other one. And only if there's more stuff, if there's more loss left over, does the second contract, the one that benefits from the first contract, actually get it. We need to be able to express that too. So those were the two kind of difficulties that we would get to be able to really handle not just insurance, but reinsurance, which is now would cover all of our client base and their needs. So we tried representing these complex ways of forming the subject inside the contract language itself. Came up with stuff like this: loss to these two portfolios, net of, meaning after reducing that loss by the payouts of those two treaties. Those are the inuring treaties. So this would group the losses of the two portfolios and subtract the losses of the two treaties. So it didn't work out very well. It changed the character of the language. The things we did to compute and to compute the subject, I mean, they were simple enough, but they were just different from what we did than what we did in computing the payout of a contract. And in a way that adding the sublimits and deductibles, that fit sort of in the context of the contract. But this really wasn't about the contract itself. It was about how do I specify what the subject of the contract is. So we came up with this idea of a position. A position is just this named, it's like a wallet or something. It's a named thing that can hold value. And contracts respond to claims from positions and pay out losses which go to other positions. So you now have these two things. You have contracts, which are this function, positions, which are this sort of named collection of losses, of quantities. Now, what we wanted to do once we said we're not going to do this within the contract, this forming of positions, we said, okay, well, what do we need to be able to do to create these what are the operations we need to be able to, given a position, to create the position that would form the exact subject of the reinsurance contract? We need to group two or more positions, basically add together the losses where they line up. We need to be able to scale all the losses, say by a factor like increase it by 20% because it's from last year and you think their business is going to grow 20% this year. We need to be able to filter out losses that don't match a predicate. Like I may have a portfolio of all the insurance contracts, or it's not even contracts, all the insurance losses of this insurance company, but some of them are from residential contracts and some of them are from commercial contracts, but I only want to cover the commercial ones. So I need an ability to filter those losses. And I need an ability to net out or subtract the inuring contracts from the portfolio lost. So now we have these two things. We have contracts and we have positions. And you know, I wasn't sure how to draw this, but because I don't remember what exactly that top one was, but I remember staring at it in this sort of corner, kind of like a conference room for hours trying things, and then it sort of occurred to me that, you know, we don't really need two things, right? We just have, you know, like these, you know, this oval and the rectangle. Really, the contract is just, it's another operator, right? It's just a function that takes a subject into a payout. It's just it's literally a function, right? It's you know, given subject X, I'm going to compute f of X, which is the payout. Well, that's really good, right? That actually provides closure of operations because, you know, we have already these other operators on positions that take positions to positions. They grouping, and this is an example now. We didn't have a language until this point, until we got rid of the fact that their positions and contracts were two different things. So we have grouping. So a statement there is gross, is direct, and assumed. So direct is your losses for the insurance you write, the primary insurance you write, and assumed is losses that you assume from an insurer by writing a reinsurance contract. So big companies can write both regular insurance and reinsurance. And the sum of that is their gross liability. We can scale, so expense is a position calculated by taking your premium position and multiplying it by 7%. We can filter, this is actually the example I gave, I think the previous slide. So I have this portfolio from a cedent, from a insurer, and I only want, the LOB is a industry abbreviation for line of business, the commercial losses from that, and I'm going to call that new position commercial. I can net out saying the gross is, this direct plus assumed, and I'm going to subtract ceded, which are the reinsurance contracts I buy rather than I'm selling them. Like assumed are the ones that I'm issuing, but ceded is the stuff that I'm shedding risk. And the fifth operator is a contract. So that's the actual function is given by the CDL, right? And it has a payout position, which is its name. We're identifying the name with the position of the payout, with that wallet of money, that quantity. And its subject is its input position. So it's just an arrow between these two positions, just like the others. So that then, I think Eric, mentioned that this is just math now. It's like we were able to reduce insurance contracts, which are pages and pages of verbiage and all these clauses that are, that lawyers may, spend their careers trying to, either get out of or craft or it's a full employment. It's a full employment act for a certain breed of lawyers. We're able to, by representing that in language, compiling that language, first we're parsing it into an AST, and then eventually turning it into a list of opcodes and indices into opcodes. We're able to sort of strip out everything non-essential in the contract by reducing everything in creating the subject of these reinsurance contracts. We now just have these well, it's called a universal algebra, which take on of operators on positions. So that just means that you have a bunch of operators, these 5, that take one or more positions and produce a single position as their output. So let me see. I guess there's time to try and do the demo. I'll have to restart it because my computer had died, but oh yeah, I'm going to have to. So that's the end of the thing, except for this demo of something that shows those two things going. So are there any questions while I'm just logging into the VPN and stuff here? No? Yeah. Hi.
Who had a question? Okay, let me throw you this. Oh. It's stuck in my hand. Thanks.
It's too much fun.
Hi. Did you use a specific tool stack for creating the DSL, like Xtext or something similar?
So we originally did it with, I used F#, partly because we were in .NET at that time. We're in JVM now, but we're in .NET, and F# had support for Lex and Yak, which they had gotten from OCaml. It sort of came free with the language. So I'd taken a course 20 years before about Lex and Yak. So I used that as tools to generate the grammar. And then I guess we hired a compiler engineer from Microsoft. Once we had validated the thing, we hired a real compiler engineer, and he immediately rewrote it stuff in Bison and C++ because he was very nervous about garbage collection, which I don't think that was ever really a problem. Eventually, when we went to Java, which had nothing to do with this, it was just a more global corporate thing, we ended up with Antler, and we're very happy with that. One of the things I'd say in favor of Antler is that the way Terence Parr did it, you just write the productions, basically, sort of the left-hand side of what you do in all these others, where you're writing the actions. So you're not restricted to actions. So you just describe the grammar, and then you can, you create this parse tree, and then you can either walk it or kind of listen as events occur on it. So that allows us to have many purposes to the parse tree. So this is the, but it's not showing. How do I, or maybe I have to finish with this. Okay, well, I had 2 more slides. So let me show them. So this is 10 years after in New Orleans. You'll see there's some missing things. This is the 9th, what was it called? It's not county, it's the 9th district, basically. It's one of the poorer districts that got hit hardest, and that's what it looked like shortly after. But this is what it looked like a year or 2 ago. So, reinsurance and insurance did, it's not always a totally positive thing, but it wouldn't have happened without the ability to weather this storm and pay $40 billion dollars in insurance claims to people who needed that money to rebuild their homes. And, and to the extent that we were able, that we and our competitors even are able to provide tools to help them manage their risk, that does improve the ability of the reinsurers and the insurers to help a community get back on its feet. And I do have one more slide, which I've been sort of using New Orleans kind of as the MacGuffin of this story. And I just wanted to show it's not all disaster, and New Orleans is a wonderful place. So it's 5:59, and I think there's an open bar. So why don't we take another question? Anyone who wants to see the prototype, it's actually written like 4 years ago, but I still run it on my machine at work. I'd be happy to show how we can use these 2 languages working together to compute points on this EP curve in seconds. This is something that took people a lot longer in the past. Yeah.
Were you able to test against the old system and the data that produced?
Yeah, well, when you say, we had to, in places where the capabilities matched, we had to be able to match their numbers, but our capabilities were more powerful than theirs. However, the data in other words, the actual contracts, almost all of those contracts on the insurance side are coming from our other system via import. So they're a subset of what we can support in CDL. In terms of treaties, we can we far outstrip, I believe, the current system. But yeah, I mean, we have a lot of customers. That's, as we said, our productive and mature system. And
So our
it's
contracts
been paying our salaries for a long time, and will for
is
some
contract, are they represented in this language today?
Yes.
Yeah.
Yes. Yeah. So all contracts in our current cloud offering, RMS1, are imported from our legacy system and stored as CDL, and then people can write reinsurance programs, which are collections of reinsurance treaties against those contracts, and then they can roll those things up. Let me see if I can. Oh, my time is up. So anyway, my time is up. Thank you, everybody. And I'm around, and I'm more than happy to show you the proof of concept. It's something I'm actually very, I don't know, I think it's fun. And it's one of the bases of what our current product is. So thanks again. I'd be happy to answer. Thank you.